Well, hello everyone. Welcome back to Adrian's Digital Basement 2. On today's video, I'm going to be working on this 286 motherboard. Basically what's going on with this motherboard is, well, nothing. Well, something, but nothing. This is not a repair because the motherboard actually, well, even though I wrote no post at some point, it does work. I tested it and it's fine. The battery leaked really badly and there's just some damage around this area, but it didn't seem to cause the motherboard to not work. Problem is, there's plenty of corrosion around here. The keyboard jack is flaky. It works, but Deoxit kind of revived it. So in this video, I want to try to just remove a bunch of the corrosion that's on here. And that's going to involve using something like a Dremel here with a little rubber tip, swap out the keyboard connector because that's all corroded. And I don't know, just make this motherboard, well, clean it up so that it's going to last. It's not like 286 motherboards grow on trees these days. This one is nothing particularly special, just a 12 megahertz 286. But nonetheless, I'd like to make sure that this motherboard stays working in the long run. And even though I cleaned up the corrosion at some point in the past over in this area, it still could get worse unless we clean it up and make sure we get all that corrosion off of there. So this is the motherboard. We can peel this off now. We don't need to worry about that. We have a WinBond chipset, a Siemens 12 megahertz CPU that is integrated into the board. Mathco processor's not installed. It takes SIPs. That's kind of unusual. Also can take DRAM. 512, I don't know. It probably allows different types of DRAM to be installed, and you have to just set the jumpers appropriately. To be honest, I haven't looked at the manual for this thing. All I know is that this is 2 megas of RAM here, and it does work. But all the issues we're dealing with here are down here in this corner. So you can see that I've already tried to scrape away some of this, and I'm pretty sure I put either vinegar or a navel jelly or something in the corner of this board, and believe it or not, it works. Even though, you know, there's plenty of small traces there that were under the battery. You can see the keyboard connector is looking kind of crusty, and on the back side of the board we also have a little bit of damage as well. I mean, look at this trace there. It could be broken. So I think what I want to do for this video, and this is just going to kind of be a chill repair video, is I'm going to use this little battery powered Dremel here with these rubber tips here, abrasive rubber. I think they're designed for polishing jewelry and stuff like that. They do a really good job at removing the solder mask, and you know, hopefully we'll eat through some of that corrosion there. We want to expose all the traces so they look good. And then I just use clear nail polish lacquer basically and coat this stuff again. Obviously, you could use that UV curing stuff. I have some. The stuff I have is green and it always looks kind of ugly. I honestly don't know the difference between this stuff and that. Like, why wouldn't we want to just use this anyways? I don't know. There's a little bit of corrosion around these parts here, so I might want to try to polish that away as well, like using this thing here. And like I said, swapping out this jack, and we'll kind of go from there. So first thing that we need to do is remove the keyboard connector. I'm going to use my Hakko 301 here. And it's always a good idea to clean this before you start, because look, there's some stuff in there. Now, if you have one of these or any desoldering iron, one thing I really recommend is getting yourself one of these little cleaning drill bits. One of the common issues is that the tip gets clogged up. And this, which I got from Amazon, it's just a little tiny Hakko drill bit that basically allows you to clean what's inside of this thing. Now this thing is on, so it's heating up right now. And okay, everything is clear. But I've had issues in the past where this just gets jammed up and it's really crusty and doesn't melt. Probably because I was cleaning up corroded solder, stuff like that, like leaky caps and things like that. But you can just sort of hand drill this and make sure it's nice and clear, which it is obviously. And it's very easy to break the little bit there. So you want to make sure that when you store it in like that. So originally I was going to try to do a repair video with this motherboard, but I didn't end up needing to because it just worked. I wrote no post on it because I had tested it in the past. It seems that was not the case. And I think what I had done is I tested it with my postcard, didn't plug a speaker or video card or anything else in, and I didn't see anything on the postcard, and just immediately stuck this blue tape on here that said no post. But the reality was it was just a bit of a dodgy connection in the slot. So when I went to go back and test this again, because I was going to do a repair with this motherboard, that was what the intent was, is I wanted to do a little bit of a repair. And I thought, okay, 286 motherboard, that might be fun, you know, battery damage. Well, figure out what traces are bad. Of course, I went to test it again, and I hooked a speaker up, and even though the postcard didn't show anything on it, it started beeping. And that tells us that it's actually, you know, running and executing code and stuff like that. Hakko makes really short work of stuff like this. There we go. There it is. Of course, it's possible to clean this up, I guess. I don't know. It's not really worth it. You can still buy these. So when it looks like that, it's better just to toss it out. These are so common and so easy to get still. Okay, well, looking under there, actually things look really good. No wonder why the keyboard worked. None of these traces are bad. It's really this area over here that's the problem. Let's get this here. Now I have the microscope ready in case we need to use it. Let's see how this does on these traces right here. I want to uncover all of these. Anywhere you see little like bubbles and stuff in the traces, like right here, I want to make sure I get those nice and clean. All right, I think this tip is not working so well. I knew that was going to be worn out, which is why I grabbed a second one. I kind of buy these in bulk from AliExpress because you go through them pretty quickly when you're doing this kind of work. Now, one thing that happens when you're using this is it gets really difficult to kind of see what you're doing. So a little IPA just sort of makes it all come clear again. So that's what I like to do, is spray that on there. So I didn't even notice that there's still part of the battery here. The little pins are in there. So I should remove those as well. So this looks pretty good. No wonder why this thing worked. Looks a little bad, of course, when it's all covered in dust. There are no breaks in any of these traces here. Everything looks good. I got definitely more sanding to do, and look down there as well. Plus some around the leads on these components right here. And then you can see like this via right here looking kind of crusty. This isn't exactly the right tip. There are different ones you can get. Some are like pointy, and those are better for getting into really tight spaces. This wide one, obviously I have to run it like at an angle like this. All right, let me get out these pins here so we can get the tool right down there onto the PCB. So for these, just get the soldering iron ready. It's going to be difficult because see how much, you know, this is all crusty and corroded there. Let's see if I can get this to come loose here. So nothing's really happening there, even though the iron is up to temperature. So I'm going to add some fresh solder on here. Hope to get some heat transfer. Okay, that's not really working. There we go, that one worked. So we heat it up and then grab it with the tweezers. Okay, I think what happened is I pushed it through the board. There it is. So that was the part of the battery that was still left behind. Let's see if we can get this other one. It's looking really bad. So when this happens and you can't really get heat onto there, I like to grab something like the engraving pen here, and we're going to just eat away at this a little bit. Underneath that kind of oxidized coating, there is some actual solder there. We just need to get access to it. Okay, there we go. Plus there's this big ground here. Takes a lot of the heat away. Come on, you are fighting. You are fighting. It's moving. Okay, I think I just pushed it the other way. Yeah, I think it's, oh no, I got it. There it is. Boop. All right, I'm gonna use some wick here to try to clean up this mess. I don't wanna get this into my desoldering iron really. So let's see if this works. Wow, it is not wicking up. Oh, there it goes. I'm using MG Chemicals Super Wick. There we go. We actually have a nice through hole now. Let's do the other one here. I'm actually just gonna heat this up first. There we go, and get this with the wick. I use the really fine braided stuff here, so with the big holes like this, it can take quite a lot of it to wick it all up, but we're getting this one. The more corrosion was on the other one. This one over here was worse. And the camera is focused on my hand. Sorry about that. Yeah, it does that. Ooh, look at that mess over here. Look at that mess. Okay, back to this side. I want to clean up these holes here where the battery was connected. Now it's very muddy and messy here. So we just hit it with the IPA again, and then of course a little brush can help just expose, what we're actually looking at here. You want to make sure that you don't see any more little bubbles in any of the traces or anything like that. Obviously, I think there was one in one of these. Ah, right there, we got to clean that. So that could be a broken trace for all we know. Let's clear that off. What can happen is the corrosion, like right here, it gets underneath the solder resistance, starts to eat away at the copper. So theoretically, if you leave that, it can get worse over time. So you want to expose it and clean it off and then recoat the traces. Now the battery was obviously connected right there. And then what you want to do for any exposed things like this is retin them. And you can obviously retin all the traces if you want, but I typically find that a bit of a pain, and that's why I just use the nail polish on any of the traces that had solder mask. But yeah, for things like that right there where it's already exposed, you don't want to put the nail polish over that, because then obviously you can't resolder onto that very easily. Okay, do we see any more dots on here? What's this here? That's nothing, a little bit of nothing. Everything looks fine. Everything really looks fine. I mean, that's why this board was obviously working, because none of these traces were actually broken. This brown here and this is flux residue, so that's fine. Yeah, okay, everything looks fine on the bottom here. I'm pretty happy with that. What's this over here? Okay, that's nothing, just a little bit of dirt. Okay, that might be a little dot there. Not that it matters so much for the ground plane as the small thin traces. Okay, whatever that was, I think it's gone now. Now you can see this is leaving a big thing of crud on the bench here. So we'll just wipe that up. And let's go and focus our attention back on the top side here. So what I need to do is hit this with IPA, and we need to brush this. So obviously we have a bunch more corrosion I need to attack. Now ultimately, it'd be a good idea if you just removed all of the parts up here entirely. Obviously I just took the keyboard connector off, but if you removed everything here, we'd have a better job at cleaning. But I think I can get this, dealt with without having to do that. Sometimes you get corrosion in the connector here. This looks fine. We can see there is a little bit right there though. There and around the crystal here. And see right there, there's a little bit there and here. So we got a little bit more spot cleaning to do around this area. Oh, look at that. There's a little bit of green crusty right there. Oh yeah, and look at this trace right here too. Wow, that looks bad. So I'm gonna go to my little pointy ones here so we can really get in there, get down to those little spots. And look, let me be honest, I don't really know, how bad of a situation this is right here and this over here and stuff like that. But I figured while we're here, it's better to just try to clean this up. Oh, look at that one there too. So it's under the keyboard BIOS chip. Right, okay. I'm really surprised this motherboard works, but these are obviously just cosmetic. Let's clean those up and see what we see. Interesting is the trace there under the slot is actually exposed. Yeah, so I could get that clean. I think the biggest difficulty is going to be right in there. Again, removing components. If you really have a motherboard that you absolutely must save, you got to remove the components. The only real way to know for sure, because I'm noticing now there's traces under here that are a mess too. Okay, we might be approaching the limit of what I can do without taking off a bunch more components here. Obviously, we have a trace that goes under this that looks like it's not super great. Where you can get a little more precision is using the engraving tool, which is just a Dremel with a very fine little bit on it. You have to be careful not to push too hard because you can actually break through the trace. But let's try cleaning up in here, for instance, because I can actually reach in there without hitting this stuff. It's really hard. So let's brush that off so we can see what we've done under there. I think there's still more to go. See how it's sort of dark right there? That's just from the corrosion itself. And actually it's definitely eaten away quite a bit right in that one exact spot. Now this is a power rail, so it's very easy to just you know, take a piece of wire and lay it across this corroded part right here without causing too much difficulty. You just have to make sure you don't touch this little crystal here. You got to make sure there's space there. And that's because, of course, I think this is grounded on the outside, and this is probably one of the various power rails. Here. I think that looks fine. Okay, what I'm going to do here is give this a better clean so we can really see what we're looking at. While cleaning up, I found a nice little pocket of green right here, hiding under this capacitor right here. All right, this is looking pretty good. Now, as I mentioned, this is always a, I don't know, what's the right word? A gamble? Like you're always gonna see stuff that doesn't look great when you look at this, like over here, things like that. But the reality is, if you really love the motherboard, then yeah, maybe remove the slot, remove this chip, this, you know, everything around here. Really make sure it looks perfect and then put it back together. The worst case of what we've done here, which is remove most of the corrosion that's happening on the board, this thing should now last. Now, it's not to say there's not some hidden underneath some of these parts and it will continue to eat away at those traces. That just means at some point in the future, if this thing does break, I'll just have to remove those parts and then investigate where the traces have failed. Anytime you remove parts from boards, you risk damaging the board in some way that you maybe didn't see. You might lift a pad or rip a trace underneath this, put it all back together, and that doesn't work at all. And then you've sort of introduced a whole bunch of new additional problems. What I wanted to make sure I did here is get rid of most of the visible green crusty stuff that was on here, which I think I've pretty much done. I think I see a little tiny bit here and there around these parts, but it's so minimal now that I think this thing is ready to be recoated and have this part reinstalled. And you kind of have to decide when you're done, because you could just keep going at this forever, and anytime you wear away at this stuff, you could accidentally eat through one of the traces that currently is still connected. The only thing I think I'm going to reinforce is that one right there, because we know we have a weak spot that was caused by that green stuff. All right, so what we're going to do is I'm just going to put some flux here. Just spread that over where we're going to reinforce the trace. And I'm going to use this resistor lead to actually bridge over that section right there. And to do this, I already tacked down one corner of it. All right, and you can see that I've just bridged those two traces. So first, let's cut away the resistor lead. Now we'll just attach the end here and try to clean this up here. There we go. Just swipe it away. Let's add a little more solder on this end. All right, there we go. Now the funny thing is, I was just trying to tin that upper trace. It's not really tinning that well because of that corrosion that's right there. So maybe we should take that resistor lead, I think the other part of it here, and we'll reinforce that top trace as well. I know this looks a little ugly, but it's better than it was. I can guarantee you that. All right, there we go. Traces reinforced. So final step, I think, is I'm just gonna give this a final clean. Do we see anything else that I really need to look at? Yeah, those traces there look a bit crusty. Look at all that. Oh. See, I wanna avoid this, like, every time I look at it, I need to do more. Okay, I really gotta stop here. All right, time to give this thing that final clean and then nail polish time. All right, I think a good strategy for applying the solder resist or nail polish in my case is I'm gonna put it only under where the keyboard connector goes. All of those traces look absolutely fine. And then I'm gonna reinstall the keyboard connector and make sure the motherboard still works. I might have broken through a trace here cleaning this up, and in that case, it's easier to fix before we paint the nail polish on. Although unlike the solder resist with the UV curing, nail polish comes off with acetone, so it's pretty easy to get under it so you can fix things. Now, I didn't say this earlier, but if you have a motherboard that's like this, I definitely recommend that you test it first before you do any of this work. You want to try to identify exactly what might be wrong with it before you start to do this kind of stuff. Because obviously, when we do this, we are potentially damaging the board, and you want to make sure that you know what's wrong with the thing first before you potentially cause more damage. So that is definitely my recommendation, and that's exactly what I did with this. I know I didn't really show it working, but believe me, it was actually working. Now what I'm trying to do here, and I goofed up a little bit, is I should have just tinned the connections there. Not the traces, obviously, because those are going to be underneath the keyboard connector. But the through-hole connections that the keyboard is going into, obviously we're going to be soldering it back on. And when we do that, it should reflow over all of that stuff. I'm just going to get this clear nail polish on here. And I like to clear specifically because, well, you can see it's similar looking to what's on the board already. And you can buy nail polish, obviously, in like green and other colors, so you can paint whatever color the board is, or at least a somewhat close approximation. But I found that this lacquer is very durable, and considering, you know, it's designed to go onto human hands, which are getting a lot of wear and tear, it's very long-lived in a situation where it's not exposed to the elements, that it is, you know, in the case or on a motherboard like this. If this lasts a long time on someone's nails, then it's really not going to have a problem when it's on a motherboard like this. Okay, I think that's good enough. Essentially, there's a lot more to do, like over here and all through here and all this stuff. All of this needs nail polish coating as well. But for now, I just wanted to make sure that under the keyboard is good. And you can see that I tried to not put it where the through-hole plates were. Are these two connected in the middle? No. I think what that is, why it looks like there's something there, is because I don't have the lacquer right in the middle there, because it doesn't need to be. Obviously, that's just the PCB material itself, and it's sort of a dull color, so it almost looks like there's a trace there between those two. But that is not the case. I can see a little bit where I missed, right in there. So we'll move these caps over here. We don't need to worry about the underside. Obviously, we can apply that after the fact. Just got to worry about the top side here. And it's looking good. I'm not 100% convinced. Like, see, there's a little dot right there that I didn't clean up. I'm not 100% convinced that that will just keep spreading forever now that the battery's been removed and it's no longer leaking. I feel that that corrosion is sort of fed indefinitely. You can see a little bit right there. I didn't clean up either. I feel that the corrosion is fed by that continual base material that's coming out of the NiCad batteries that just allow and facilitate the continual corrosion of the PCB. Now, if you have any scientists watching who are very familiar with the chemical processes that allow the leaking NiCad to eat away at the traces, I'd love to hear more. I've obviously treated this already with vinegar, which sort of seems to neutralize it at least, or I think I used navel jelly, which is a very powerful version of an acid that just eats away at corrosion and stuff like that and kind of stops it. But when it's underneath things like there, it doesn't get to it, obviously, because it sort of sits on the top. Okay, well, anyways, time to let this fully dry, and then the keyboard jack can go on this new one. Okay, well, I let that dry, and I reinstalled the keyboard connector. So what we need to do now is see if this motherboard actually works. And I want to do that before, as I mentioned, because if we do have any problems where I broke a trace by cleaning here, then we're going to need to be able to, well, it would be more helpful when they're exposed with using the multimeter to try to find continuity. That's basically your strategy. If you have a motherboard like this that isn't working, to fix the motherboard, you have to, well, the main strategy, because we don't have schematics here, is to start to look for any broken traces that might be on the board. And to do that, you really have to either use a microscope or something like this, a magnifying loupe, or even what we're doing here with the camera, and start to really look for anywhere where there might be a break in a trace. Now, that's not broken, it's just the angle we're looking at here. It's kind of a darker color, but that could be a break, or you could have a break right here where the trace meets the via. And what you need to do is, using these little bits on the Dremel here, you clean that off, and that exposes the break. And remember how when I did it here, we could see big chunks missing, right? Well, you might have little chunks missing here or there, and you just use your multimeter and you do continuity. And now this is cleaned off, you can actually poke the trace right here and at the via, and you could do the same over here, there, and there. And if that little spot were actually a break, we would know that. And then you just need to reinforce it, either using a piece of wire like I did right here, or you could use a bodge wire. You could do it on the bottom side. And you just have to be methodical about it and go through and look very carefully for anywhere where you see corrosion, clean it off using that rubber bit here, if you can, if it's not like underneath a component or something like that, and then replace it if it is broken. Now, it could be something that runs under here. You notice like these I can't get to. And if you don't want to take this socket off and we suspect or you see a bunch of corrosion here, then you need to kind of try to figure out where these traces are going. Probably if we flip the board over, you're going to see a bunch of vias right there. Let's just do that. This right here is the underside of that surface mount chip, and you can just see tons and tons of vias here. So if you have a trace that's coming out, say, of the chip, that surface mount chip, and it's going underneath here, it's probably going to one of these vias, and then it has to make its way down. So you should be able to find it theoretically. Worst case, you got to remove the chip and that socket, or just remove the chip and then you could like see through the socket. But if you can't, then you got to remove the part and try to trace down where it's going and where that break might be. Since there's a ton of corrosion and we can kind of see it went along the top edge of the board right here, so I've sanded that away. It didn't seem to have affected anything here. You can kind of just look for where things are green and crusty. Remember, there was a lot of green and crusty all here, around the crystal, sort of around this part of the chip right here, obviously the keyboard connector, potentially this ISA slot. Is that actually bad? No, it looks the same all the way down there. I was just trying to see if this was suspicious there. But you see, even underneath here, there's a little bit of evidence of corrosion. So that is the area you want to focus in on. Now the issue is, of course, is you could have a problem. The CPU might be bad. There might be a bad crystal, things like that. So it's worth checking that stuff first. Make sure the reset circuit works. Although, now I think about it, I think the reset circuit is actually coming from this chip as well, the keyboard BIOS. So if this thing is not working, I think the computer never even comes out of reset. And if you have a bad trace over here, it could be the reset line. That is the case. That is bad. Although reset might be coming from one of these. I'm not 100% familiar. It may be worth checking the schematics for the IBM 5170, which this is obviously a clone of. I mean, what they did is these chipsets here took all those chips on the 5170 and condensed them down into these chips. So most of that discrete logic is gone. But from a fundamental operation standpoint, it's very similar. So if you look at the 5170 and it says reset is coming from, you know, some specific chip, then I guess that reset line is probably inside one of these ICs. But if it says it comes from the keyboard BIOS, which I can't remember if it does or not, then suspect that we have a broken trace. That's why I suggested you should always test the board first, because if it has some signs of life but say just the keyboard doesn't work, well, if the keyboard's not working, but it shows otherwise it's signs of life, you could have a bad connector, this could be bad, the socket could be bad, but then more likely, because of all the corrosion, we have a bad trace. We need to test this thing just to see if it's actually working before cover up the rest of these traces. So I'm going to be using my ATX power supply here. We'll just pop this on top, and we'll be using a post analyzer card. I highly recommend you getting one of these if you're doing any kind of PC troubleshooting. And I highly recommend plugging the speaker in, unlike me when I first tested the motherboard and was tricked into saying it wasn't posting, when in reality it was fine. And part of the issue is these cheap postcards. See, this is just, I don't know what this kind of coating is. I guess it's like a lead tinning or something like that. It's not very good. It's not the most conductive thing in the world. So these slots might be just dirty, and maybe I wasn't making good contact. Because when I went to go test this motherboard again, definitely had dashes, but I heard beeping when I had the speaker hooked up, and then I just jostled this, and all of a sudden I could see postcodes. And here we go. 3, 2, 1. Nice. Okay, so we're getting beeping. And anytime you have beeping, I'll just unplug that so we don't have to listen to it. Anytime you have beeping, that is coming from the CPU executing code out of the ROM BIOS. It will not beep like that if it weren't for the CPU running and the ROM BIOS being there and available. So that tells us a whole lot about this motherboard. We have a good clock, we have a good reset circuit, we have a good 5-volt rail because that's what that stuff runs on, obviously, and we have the chip select for the ROMs working, and the ROMs themselves have good content on them because, you know, that might be missing. If we pull these out, then the computer will look 100% dead. It's not going to beep, it's not going to do anything because you need good code to execute for the CPU. So there's a lot of constituent parts that are necessary to kind of come together to get the system to at least get to this point. Now, the RAM is not even necessary. You could have the RAM out, and there's enough capability in the ROM BIOS on these later AMI BIOSes to at least make the computer beep. So you should see a code on here, like 1 or 2, a low number, because this counts up as the diagnostics run, and then you'll just get beeping to tell you that there's no RAM and it can't proceed any further. But what we're seeing here, and that beep code, I'm very familiar with it, it means that there's no video card detected. And AMI BIOS needs a video card for the system to operate, so that's why it halted. So what we're going to do here is we'll just pop in this VGA card I have sitting here on the bench, ISA VGA card, and let's make sure we're on the video capture device. Yep, there we go, Extron 300A, which is what I'm connected to, and we power this on. Oh, I need to plug the keyboard in, which I happen to have sitting right here. All right, it's going. It is going. So plug this keyboard into our newly replaced jack, and I hit escape and it actually skipped the memory test. So cool, that's working. Yep, there we go, look at that. Right, so there we go. We have some stuff in here, and it looks like this motherboard supports BIOS shadow ROMing, or shadow RAM. That means it takes that upper 384K of RAM, and instead of mapping it to extended memory, it maps it into that same upper memory space there. And then there's a function in the BIOS code that instructs the chipset to copy the ROM BIOS, which is up at the top of the memory space, into RAM. And the RAM is much faster than these slow ROMs. Once it's in RAM, a flag is set in the chipset to tell the, chipset to map any reads or writes, reads really, from that ROM space. Instead of going to the ROM chips themselves anymore, it goes to the RAM. And that's much faster. And actually any code or any operating system you're using that's using BIOS code or BIOS calls for anything, there's a bunch of calls in BIOS for printing to screen and stuff like that, will be sped up dramatically. Now, if this thing had like Microsoft Basic on here and you did the shadow RAM thing option here, it would actually speed up Basic dramatically because it would be running it from RAM as opposed to being in the slow ROMs. Also, power on high speed, so I guess maybe it inverts the turbo jumper function. So if it's not installed, it defaults to high or not, or I don't know. It says power on high speed enabled or disabled. It's kind of vague. And then EMS function is an extended memory or expanded memory. I can never remember which one it is. I think it's expanded memory. It was an XT memory standard to allow XTs to go above 1 megabyte, and it takes 64K in that upper memory space, in that upper 384K, and it maps that into another set of RAM. So say you have 8 megs of EMS RAM, then that 64K is a window into that upper memory, and it allows the program to page through this upper memory. And early programs, Microsoft Windows and Lotus and stuff like that, supported that type of memory on XTs, and this is compatibility of that for this 286. It would need a driver though, which I don't have, although it could be just a typical WinBond driver because this support is built into the chipset itself. So just looking around for this WinBond chipset might reveal another motherboard where those drivers are available. We could probably use that. Now there is no battery in this computer right now, so obviously saving this isn't really going to do anything. Let's look at those diagnostics. Hello, there we go, diagnostics. So there's some built-in AMI diagnostics here. They're very basic. There's a keyboard test, some video tests, printer and modem port test, and I can't do hard drive or floppy because those aren't configured. If they were, there would be some rudimentary tests for hard drive and floppy. It's kind of nice that this is here. It's like the most bare bones tests available, but if you have no way to boot the system, then yeah, it's perfectly good. Now, as I was just saying, because the battery's not installed in this CMOS and clock chip, which is this one right here, would just lose the settings after, I don't know, several minutes or whatever it is. There are a few different options. I think I was trying to talk about this before. We could obviously replace, put a new NiCad battery in here, and if this charging circuitry stuff is good here, it would just work as before. Of course, I would not recommend doing that because then it could just leak. The other thing you can do is install a CR2032 battery holder if there's enough space here and stick a CR2032 in there. Problem is, this circuit is designed to charge that battery. So you can do a couple things. Instead of wiring it into the motherboard, you can wire it to this connector here, which is designed to take, there's a pin there, isn't there? It's designed to have a non-rechargeable external battery connected to the motherboard. So you could connect it there. Next solution you could do is if you want to have the battery holder right on the motherboard, is you just need to disable the charging circuit, which is usually facilitated by a diode. So we have a couple diodes on the board over here. One of those is going to connect the battery circuit here to 5 volts. And by simply just removing that diode, you've broken that connection, and now this battery will never be charged, and it will simply power up the clock chip and the crystal oscillator that goes with it, which is over here. Sometimes you have an extra chip like one of these that's also powered up, and it does drain the battery kind of fast. So I don't think that's necessarily the best solution when you have just a CR2032 running this whole circuit over here. The next thing you could do, of course, is replace the clock chip. You could put a Dallas chip in here, it will just drop in, and then you don't have to even worry about this stuff over here. And those are really good and they're very efficient. Or you could build up one of Necroware's clock replacement modules, which are a little PCB with a little surface mount chip, crystal oscillator, and then it has a battery holder on the top. And those things are super efficient in that the little clock cell battery that's on there probably lasts 15 years and not ever run out of charge. So that's a really good solution. His project is entirely open source. You can buy those chips on like AliExpress or whatnot, and then you can have the PCBs made and you can have the little crystal. You can buy all those parts pretty easily. And it's relatively inexpensive, and I do recommend that over a Dallas clock chip. Unless you happen to have Dallas clock chips laying around, you can modify them to remove or disconnect the internal battery and add an external battery. They are very efficient again, so they last a very long time with like a CR2032. And really going that route is probably a way to make this whole thing last a lot longer than trying to use a CR2032 in this position over here. And the funny thing is, my IBM 5170 over here, I tried originally running that off a CR2032 and it worked. It's just that it would drain that cell very quickly. I mean, 6-8 months and it would be dead. And it was really frustrating because it's hard to open and have a monitor on top of it. And I was really annoyed by that. So I actually ended up putting one of Necroware's clock modules in that computer because I just wanted to do away with having to constantly replace the battery. And that absolutely did fix that problem because, like I said, those clock modules last for years. And that's obviously desirable for a computer that I actually do use from time to time. And it's not something that is just stored in a, on a shelf somewhere where you could just take this CR2032 out anyways and just put one in if you're going to be using it. Now, if we look at the clock chip that is on here, this is a Hitachi one, and I don't actually know how efficient these are, but this is from 1991, so maybe this is somewhat efficient. The earlier Motorola ones, which I think is what the IBM uses, and one of the support logic chips, is just not super efficient, and that seems to drain really quickly. So your mileage may vary on that, but for this motherboard, I'm trying to think. I'm not going to be using this. This is going to be, one of my spares. So I think for now, I'm not going to do anything, and I'm just going to paint all of this up right now with nail polish so we can get this thing ready and just do some final tests with it once I've done that work. Now you might be wondering, what's the oldest motherboard that I've done this work to, this kind of painting stuff on? And I have some that I did years and years ago, and they're still 100% fine. No issues whatsoever. I don't really know how long it would take to, for this corrosion to really set in and become worse if it were gonna do that. Oops, I just got some nail polish on my finger there. But like I said, I did some of these ages ago, and they're still totally fine. One thing that's good about the nail polish is it actually brings back a bit of the shine. The polishing kind of takes away a little bit of the shine of the original coating that was on the board. And painting it kind of brings it back. Okay, this is looking good. This thing should hopefully be protected in the long run. And while it survived, it was a survivor as it was because it didn't get damaged from that horrible leakage. At least it shouldn't get worse now. Well, I think right now I'm going to leave this toothbrush underneath here just to let this dry on both sides. And we'll come back and we'll put this thing through its final paces. All right, things are looking good. This thing is all dry and shiny and protected now. And I think what I'm gonna do when I talked about all the battery stuff is I'm gonna just install a battery holder into this. And notice this thing actually has holes for different sizes. Now positive's over here, but there are 2 negative holes. And I'm pretty sure the original battery was connected to this one right here. But there's this one here that's a little closer. And what could that possibly be for? Well, I think it's for a battery holder. Let's just see if this actually fits into the board here, because I think it will. Maybe. It's in there. Now remember, I talked about the fact we can't just put this in here and have it all work perfectly because of the charging mechanism. We'll figure out how to disable that in a second. First of all, let's just solder this down. Just use this little tiny piece of solder that I have sitting on the bench here. First we'll do the positive side. And now the negative side. Ooh, hot. That wasn't quite enough, so we'll just use a little more here. Now when it comes to the charging circuit, let's look a little closer here. So the positive side of the battery holder, which is this, probably goes to that jumper. And this is gonna be this external battery, and usually there's a jumper to select between the external battery and the internal battery. Now if we flip this over and we look at the positive side, yep, there's that 3-pin jumper set up right there. And you can see that if it's on the position here, which is where the jumper is installed, the 5 volts or 3 point whatever volts that comes from this will go here to this part, which goes to there, and let's look at what those are. And then this external battery holder here is connected to that component. We can also see on this side that that middle pin, which we know is connected to the positive here, makes its way to this resistor, which then goes to a diode. I bet you this right here is very specifically the charging circuit. And we can tell that by looking at this diode here. This side of the diode should be connected directly to 5 volts. Yep, it is indeed. So the 5 volts goes to this, there's a diode drop, and then it goes through a resistor, and then that actually is what charges the battery. Now the other pin that we saw coming from here, I think goes to one of these components. And the issue is, of course, is that, there we go. I was gonna say it would be hard to make contact with that because of the nail polish I put over there. I'm pretty sure this goes to the clock chip, like this powers up maybe through a transistor or something, this stuff over here. And I'm positive that it's gonna be this that's the charging circuit. So we'll be able to tell by powering up the motherboard, we'll see 5 volts on here. And then if we remove this diode right here, the 5 volts will go away. I'm plugging in the power connector, but just to double check here, we'll turn the motherboard on. And if we take a look here at this, we should see 4 point something volts. We do, and it's gonna be coming through here. We should see 5 volts or so there, yep, and there's a little bit of a diode drop. So let me remove this diode here. I could just cut that trace, but it's just easier to remove the diode entirely, and then we should not see 5 volts on here when the computer is powered up like it is right now. Now in the past, before I really thought about the way the charging circuit works, the way I would do this is I would install an inline diode to the battery holder. But that's silly because that actually creates a voltage drop from the battery to the charging circuit, and that's just wasting power. So you might as well just remove and disable the actual charging circuit itself, which is this diode, and pull the diode out. This should come out now. There it comes. Just wiggle this, there we go, popped right out. I can reinstall that if I needed to, but it's just a normal diode, so no big deal. Now we just need to double check, so we'll turn this back on. Get ground off this terminal here. We're still getting 5 volts there. Okay, well that must mean that this diode over here is where the 5 volts is coming from, or one of these two, whichever of those two was actually connected. What I need to do is go look up the pinout of this chip here, and we need to find where the power gets from the battery to this. If it went through these parts or went through these parts. All right, here we are on the retro web. Here it is, 6818, any brand or multi-brand 6818. They're all pretty much the same. Checking the data sheet, VCC, pin 24. Just want to make sure there's no other input here. I wonder what PS is. The power sense pin is used to control the valid RAM and time in register C. Okay, so this is how the system is able to say, oh, you know, invalid clock time data, whatever, must be able to read that pin. During power up, PS pin must be externally held low, and it looks like it goes high when it's detecting that, you know, it lost power. Okay, so it's definitely the VCC pin we need to look at. Okay, what I'm gonna do is I'm gonna pop a battery in. Obviously this is not connected to power. So let's just see if we're getting any power over here on this chip. And here it is, 3.182 volts. I was kind of thinking, having removed that diode over here, that we wouldn't. So my assumption is that when the board is powered up, maybe we have some leakage current on here. Maybe what I need to do is, we're gonna power this. Nah, there shouldn't be any leakage. I was thinking that maybe there's a diode here that prevents the 5 volts going to this chip, because this obviously will get 5 volts when you turn on the system, prevents that from getting back to the battery. And this is a separate circuit that charges it, but there was something here that prevented it from going back. But that doesn't seem to be the case. So if we put this, so we put that there, there's our 3.2, let's turn on the computer. It didn't go up at all. It didn't change at all. So the computer's on now, and nothing changed. Let's take the battery out of there. Yeah, I'm just sort of thinking that maybe what was happening is there's just extremely low current that we're measuring there with the multimeter. So we'll turn that on. So we're getting the 5 volts there. Okay, what I'm gonna do is I'm gonna take this 460 ohm resistor, and I'm gonna connect one side of it to ground, which is right there. And what I'm gonna do is I'm gonna turn this on. I'm gonna try to do this while holding a bunch of stuff in my hands. Okay, so there's our voltage. I'm going to touch this to 5 volts here. Yeah, look, it went right down to 0.0013 volts. So the 5 volts that is available there is extremely low current. Let's do that same test, but this time we'll use a 10K resistor, because that will really show us how current limited the 5 volts is there. So we'll power this on again. All right, so there's our 5 volts. Take the 10K resistor, touch it to the positive terminal. Yeah, 0.03 volts basically, and that's through a 10K. So we're talking very, very little currents available there. So however the voltage from the battery makes its way to the chip here on pin 24, it's going through this circuit here, probably this transistor and stuff. And I guess there's a little bit of leakage through this, but I think that is so slight that that is inconsequential to this battery here. And even though it's, you know, technically charging, so to speak, I think it's essentially not charging. And we can just validate that again real quick. So we should see the battery voltage. There it is, 3.97. The motherboard's off. And let me turn it on. I mean, it doesn't even go up at all. I suppose it does go up ever so slightly, because it's hovering between what, 6 and 7 there, the last digit. I turn on the motherboard. Look, it's going up to 8, maybe. Yep. I mean, barely. It kind of is. Now, if we go to pin 24 on this IC, it has 5 volts on it. That's coming from the motherboard directly. I mean, I guess, I don't know. This is gonna be fine. I can't imagine this tiny amount of current that's going to the battery here makes any difference at all. I'm very confident that this diode that I removed here is the primary charging circuit for the battery, for the original NiCad battery. And my assumption is if I move the jumper here to the other selection, which should be turning on this thing here, that's probably going to result in a similar amount of charging for that battery, because we do not seem to have any voltage here at all. Nothing. How about here now? No, nothing on there with that jumper switched over. Of course, on the jumper itself, we have 0.937 volts, which is very similar to what we were seeing on there. All right, looks like this pin goes to here. Yep, which goes to this side. And let's try to figure out where the other side of that top diode goes to. All right, goes to that component right here. All right, goes to that component, which, does that make its way down to the big chip? Yep, I think that's it right there. I think that's pin 24. Yeah, that's that. I think that's coming from, I think it's coming from that diode. It is. To there. All right, so it looks like they actually run this battery through an extra diode that this one does not run through, because the positive on this battery goes to that pin, which then is looped to this pin using a jumper, which would normally hook it up to the charging circuit, which I've disabled. And that makes its way to this diode here. This side of the diode for the coin cell goes to here. Yep. And that goes to this and goes to this transistor here. And I think it was the middle pin here makes its way to this resistor, which goes up to here to another transistor. I think that's a different transistor. My assumption is it makes its way to this thick trace, and this is the trace that's carrying the voltage down to that chip. So the reality here is that, yeah, this still is charging that battery ever so slightly. So I think what I need to do is remove this resistor right here, or diode, it's a diode actually, remove that diode and put a tiny bodge wire from here to there. So that means that this battery, when this jumper is installed, is working exactly like this battery, and therefore it won't charge this at all, but that should still make its way down to the clock chip. Because without a doubt, the 4-pin battery here goes to there, to there, to there, to there, and this goes to the clock chip. That's the power pin on the clock chip. So I've gripped onto one side of the diode with the hemostats. We'll just heat this up here. Should pop it out. Okay, it's out. And the other side, there we go. You know what, is that a capacitor? No, that's a diode, looking at the marking on the board there. It's pretty cool, it's like a glass cylinder. Let's just check it here. 0.3. Huh. This other diode is the one that was for the charging circuit. That's a 0.6. That's more what I would expect. So I guess this is a Schottky maybe. So yeah, okay, well, anyways. So with those out, now the battery, if I put the jumper back on, it's not fully connected yet because we have to bodge between that hole there and the pin above it there. So I'll just use a little piece of an offcut from a resistor or whatnot. I got it in there, and I'll just wrap it around the other pin. I'll just heat that up real quick. It's always good to like keep your little offcuts in a little container like this if you ever need extra pins and stuff. All right, so back to this. So this terminal here goes to that, and that should make its way to this top diode, right? I push hard on it because I have some of that paint there, which goes to there, which goes to there, which goes to there, and that should make its way down to the chip here. Let's see what happens. So battery's in. We should have 3.28 or whatever there, and we should have it here as well. Oh wow, that's some serious drop. So is that happening because we have two yes, okay, there are two diodes here. So I didn't even think about that. So we're getting 1.2 volt diode drop right here between these two diodes. They're just in series before it gets down to here. And I think that's because this was originally a 6 volt battery and they're trying to bring it down to 5 volts. So I'm gonna remove these two diodes. I'm gonna put back in this, this little glass one that I took out here, the one that was attached in this position. And then I'm going to jump over that one. And that should give us a much less diode drop. And then we should not be charging this thing at all. So this is kind of par for the course. This charging circuit's just sort of different, one motherboard to another. And I've worked on these before where simply removing one diode from the charging makes it all work. Like this part of it here doesn't back charge the battery at all. But on this one, it appears to. So first of all, take that little jumper link off that I put on. And I'm going to remove this other diode while we're at it. So first I'll clip onto this one. There we go. So we're not going to be reusing that diode. Now I'll clip onto the other one. That's the other diode out. These are normal 0.6 volt ones. And we're going to be reusing this diode here, the one that was in the top position, or the middle position, I mean. We're going to use this one in the top position now. So this top diode here was originally a 0.6, and that was for the external battery. I'm going to connect this from that pin there, but down to that lower pin. The reason why is it'll eliminate the need for me to even have that little jumper that I had on the board there. So that's going to go from the positive here to this jumper to that pin to there. And all I'm going to need to do is install a little jumper link from there to there, just to jump over where that diode was. And now we should have just this 0.3 or whatever this is drop to the main clock chip from this battery. Okay, if we flip this over, so there's that diode and there's that jumper link. So that's eliminating that diode. Now with this in diode drop mode, we can go from the battery here down to here, and there's that diode drop, 0.35 volts. So putting in this battery, well, first of all, let's plug this in, turn on the computer. We should not see any voltage at this terminal any longer. So power on the computer. Okay, everything is good. And we test from here to the ground pin. And we have voltage. Is this not a good diode? I mean, that's the only explanation. It's gotta be a bad diode. There's gotta be something wrong with this. Or it's not a diode. It's gotta be a diode, right? Or it's got like some serious leakage or something like that. Here, I can just test like this. So there's one way, 0.3, and switching the probes around, nothing. Absolutely nothing. Well, I'm confused. I am quite confused. Okay, so that diode is lifted. Let's check for 5 volts here. There's gotta be something I'm missing. There is not 5 volts there. And let's check for it on the, oh, the diode is sort of loose now. Yeah, that thing is passing 5 volts back through it. I don't get it. I don't get it. Let's replace this. So these are shot keys in my hand here. And if I check the diode drop on this one, 0.2 volts. So let's try this one. I feel like I am just making a big mistake here. Like I don't know what I'm doing, which is quite possible. So I'm gonna put this in at an angle, just like I did the other one. Okay, so we're still in diode drop mode. If we go from here to there, 0.21. Okay, that's kind of what we expect. That's because there's the shot key and the jumper, and it goes through that thing there. And when we power this up, I don't think we should see 5 volts here. So ground, we still do. Okay, so there's gotta be something I don't understand about shot keys. That a little bit of current must pass through them backwards. Yeah, that's the only thing I could think of. Let's go look that up. So I asked Google Gemini if it passes current. It says that They are designed to only conduct current in one direction and will significantly restrict current flow when biased in the reverse direction, although they may still leak a small amount of reverse current compared to other diode types. Key points about Schottkys: limited reverse current. Schottky diode is reverse biased. It will only allow a very small amount of current to flow, which is usually considered leakage current. Due to their fast switching characteristics, Schottkys are often used in circuits where rapid current direction changes occur, but the reverse current limitations should be considered. So I guess when all else fails, let's see if I can see a part number on these that we can look up. 5819. Right, so these are good up to 40 volts, way more than is actually needed. Good up to 1 amp, also way more than would ever be needed. And I see reverse voltage rating. Oh, maximum average reverse current at rated DC blocking voltage, 1 milliamp. And that's at the max reverse voltage. And we're not even near that. That's 40 volts for this part that I put in. Wondering if there's a graph. Percent of rated peak reverse voltage. All right, so at a normal like room temperature, which is what we're operating in, and we're at like, I mean, it was 40 volts, right? Was the peak, and we're like at 5. So it's somewhere down in here, like less than 0.01 milliamps reverse current, which is nothing, right? It's got to be nothing. So I guess the question goes out to the electrical engineers here, the people who actually understand electronics more than me. Is it okay to have a CR2032 with 0.01 milliamps of charging going into it? Is that okay? I'm assuming it's fine. Maybe it wouldn't be fine if you ran this thing for, continuously for 10 years with the battery in there. I don't know. It's a good question. I really just do not know. But I think today I learned something, because I honestly didn't realize that Schottkys have some leakage in the reverse direction. So this Schottky here that I took out of the motherboard, even though it's a bit corroded, it's okay. And I'm gonna get this bag and I'm gonna put all the Schottky's in here, including the one I just took out of the motherboard. So if I ever need a Schottky again, I'll just need to write on here with a marker what this is. I'm sure I misspelled that, but that's good enough for me. Yeah, I keep all my diodes in these sort of little bags here and stuff. And for whatever reason, I thought I had some smaller little Schottky's versus this one that's good for 1 amp or whatever this is, but it's fine. Anyhow, like I was saying, is it okay to have that little amount of charging current on one of these CR2032s, or is that still just a bad idea? All right, well, I think at this point, I need to really put this motherboard through its paces. Now that we have a clock battery on there, it's going to retain its settings. I am going to toss out these diodes that I took off the motherboard, these non-Schottkys, because they're super common, and these have a little bit of corrosion on them anyways, so goodbye. And ultimately, I know I modified this motherboard, but all I really did is I just eliminated these extra transistors and stuff, which just means that this battery should just last a little bit longer anyways. And probably what I should have done before I installed this little jumper link here is measured the current draw while the motherboard's turned off of this and whatever circuitry is associated with it, just to see, well, we could do some calculations to try to figure out how long this battery is going to last, because I still think it's probably a better idea just to replace the entire clock chip with a lower current draw one that has an integrated battery versus even relying on any of this stuff at all. And that's what I was talking about. If this were your motherboard, you have many different options here for getting this thing working. NiCad battery, external AAA battery pack that could leak, so I don't recommend that. You could do what I just did here. And obviously the way it was originally when I just removed the charging circuit was fine. I was just getting tripped up by that whole Schottky diode reverse bias stuff that I didn't really fully realize, to be honest. Or just swap out the clock chip here for a Dallas chip, or of course you could just do the Necroware one as well. You have lots of choices, and this was the one that I did. Of course, the other thing I could do with this, but I'm not going to because I have another 286 motherboard I use, but if I ever went to start using this regularly, I would definitely swap these out and put SIM sockets in as well. It has the footprints that can accept them, because I really do not like SIP sockets at all. Not a little bit. Anyways, let's get this thing hooked up and booted so we can do some actual tests with it. Okay, ready to go. VGA card, PicoGus, IDE card with compact flash card. I have XT IDE BIOS on this card, and I have my post card there. Battery is in, keyboard is connected, 2 megs of RAM's good enough for what I'm gonna do. let's power this thing up. I don't need to define the hard drive because I'm using XT IDE, so that doesn't matter. Primary display, we'll do VGA, keyboard, we could say installed, whatever. We'll turn on the BIOS shadow, which will speed things up, and we'll turn on high speed. And we're gonna check the speed to see if this thing is working. I also need to know if this is a 1 wait state or a 0 wait state motherboard. So there it goes. It's found the compact flash card. That's excellent. Okay, it's booted up. PicoGus, looks like I need to flash the firmware on the card. I must have been using a different one with this or something like that. Speed 600. Let's see how fast we're going. VGA card is fast. All right, I think this is a 0 wait state motherboard. If this were a 1 wait state motherboard, 12 megahertz clock speed would result in more like 14 or 13 megahertz in here. So that's not bad. There's probably a jumper, and if we go to RetroWeb, we'll probably find the manual that allows you to set whether it's 0 or 1. Let's just quickly take a look at that. All right, I always screw up when I'm searching for stuff on the RetroWeb. So let's see if I can figure this out. WinBond 83C201. Here it is, 2D6 chipset. Good. Not sure what else to put in here unless we do expansion slots. Let's do that. 1, 2, 3, 4. This has 5 16-bit slots and 1 8-bit slot. So we can go 5 16-bit, 1 8-bit ISA. Okay, I think that should help us narrow it down. We have 3. Oh, there it is. Well, wait. We have 2. It's just one has SIM slots and the other one doesn't. But they're the same. This looks identical. Yeah. Oh, also has a socketed CPU. That's way better than this junk. All right, so this is an Aquarius system / BCOM ham / 12W2. And well, and it looks like, I guess we actually have 3 of the same board in here. Let's open up these other 2 as well. This one has SIP sockets, so that's similar. Soldered CPU, but it's funny, the SIP sockets actually have little connectors that this one doesn't have. This has RAM installed on the motherboard, but no RAM in the SIP sockets anyways. Looks like it maybe had battery damage. No, actually it didn't. I don't know why those are tinned. This must have never even had a NiCad. It always was connected with this. This all looks the same though. All of it looks the same. There's the charging circuit. So they didn't install a NiCad or the jumper, but they installed the charging diode. They could have saved like all of 2 cents. Meanwhile, this one obviously had a NiCad. Wow, that's what could have been. Oh dear, what a disaster. So this doesn't also have the jumpers either, which is weird because I've obviously, oh, it didn't have a NiCad. It freaking had an external battery that just completely destroyed the board. What a freaking disaster. Okay, well, these 2 seem the same. This one has a math coprocessor on it and an AMD CPU, and this one has a Siemens CPU on it. All right, let's look at this final one here. Is this the one that matches what we have here? Let's see. No, this one's socketed. Siemens. Oh, look. Ha! Nice. The Necroware clock module. That's one of the other options I mentioned. And this one obviously had the NiCad because there's the jumper. And yep, there's that Schottky diode that goes with the NiCad, all that kind of stuff. It's so cool. This one is socketed. Means it can be overclocked, which obviously this person has done because they put the crystal in a socket, which has a zip tie over it. And this is a 16 megahertz chip, so absolutely it's going faster than it needs to. Well, faster than it needs to. It is sped up, and an AMI, and but yeah, this is definitely it. Minimal corrosion though from that leaky battery, but I guess they just figured it was easier to go that route. Anyhow, let's see if we can find some documentation, because that's what I really want to know. There is none for this one, but I assume these are all identical. Engineering notes. Notes from Vogons here. AP5, why is it necessary is not clear. It does not affect anything. Okay, goes to the jet key BIOS. Parity ECC on or off. Well, it's not ECC, but it's parity. Power good, detect from board or detect from power supply. Wow, that's funny. There it is, JP12, RAM, wait state 0/1. Plus you can set the FPU, whether you have it fast or slow. Awesome. And then there's a jumper here that takes away 128K, probably for EMS memory or shadow RAM. Yeah, that's exactly what that's probably for. So I guess you need to set this appropriately if you want to get the speed up probably from the shadow RAM. It's hard to know exactly. I just looked at JP12, it's 3 pins, and it's set for 2 and 3, not 1 and 2. And it doesn't say on the dock how changing that jumper affects things. So unfortunately, my bench camera has run out of battery. So I'm just gonna turn this off and I'm gonna switch the jumper to the other position. And I assume when we actually get this thing booted, it should be a lot slower in speed 600 with the jumper set to 1 wait state. 13, yes. Now can I change this on the fly? Let's see. Taking the jumper off does nothing. It changes on the fly. That is cool. Oh, it crashed. Okay, so going from 0 to 1, or going from 1 to 0 worked, but the other way around did not. What we know for sure though is that the turbo function in the BIOS does work, and this thing seems to be working. So hopefully that bit of work I did with the nail polish and everything has done the trick, and this thing will last and not die or whatever. So I'm gonna plug in the speakers and we're gonna try some stuff out. All right, so I need to reflash the firmware on the PicoGus. I want it to be a Sound Blaster right now. There we go, programming. This PicoGus is so great. It's such a good sound card. I need to make some proper menus in my auto exec here. I just have these little things, I just rem them out. So PicoGus, Sound Blaster, that's what this one is for, which has the right environment variable for Sound Blaster, and it will initialize the card correctly. So we'll reboot now, and then we should have Sound Blaster mode. I always forget how to make menus with ConfigSys and AutoExec, although I know there are plenty of guides, and like Phil's Computer Labs has a good thing for that. Okay, there we go. It's working. Sound Blaster and AdLib compatibility mode is working. So we can run the AdLib jukebox here. Let's see, we'll play some AdLib music. Great, that's working perfectly. Sounds excellent. Excellent emulation in my opinion. And it's just so great, I can just switch cards on the fly. Do I want a Sound Blaster? Do I want an AdLib card? You know, it's just, it's that easy. I love it. Oops, I'm just trying to exit out here. F9 for quit. All right, so let's run Mod Master here. So this is a 286, a slow one is that, but we should be able to play mods, and it's detected Sound Blaster 2. And I need to make sure I play something that's not gonna get me copyright flagged, like Second Reality stuff will. Let's see. Yeah, it's a little scratchy. It's mixing at 16 kilohertz right now. And I think this is a mono, Sound Blaster 2 is mono, but it's working. Let's run some Planet X3. It's only AdLibs, no Sound Blaster support with this, but that's fine. Works well. It's fast too. Yeah, 0 wait states, 12 megahertz. It's great. Okay, let's try Ultima 6. I think it's configured for VGA and AdLib probably. It's loading still. Switch the mode here. 1990, so it's right around the time that this computer would be contemporary, although this was a cheap computer. Oh, why is there no? Oh, I guess I don't have the sound configured. Video's working, obviously. Actually, the ROM BIOS date is 1990, so that was perfect timing for that game. I kind of forgot how this works. Do we want to install to the hard drive? I don't really want to install this. So these are the various video modes. We don't have a mouse hooked up. Oh, okay, here we go. MT32, Tandy 1000, Creative Music System, which incidentally, this card can also emulate, and an AdLib. So we'll do AdLib. It's the normal port. It says correct, yes. Start a new character, save the information and keep your character. I don't think I have a character on there anyways. Okay, maybe now it'll work, possibly. I'm not sure I've ever tested this with the PicoGus. Maybe it doesn't fully work with it. Oh no, there it goes. I'll switch the mode. Great music on this game. All right, I rebooted the system. I wanna try that game with the CMS sound. I don't think I've ever done that. And since we can switch this PicoGus on the fly to CMS, let's try it. Okay, so here's the CMS firmware. I'm sure Ian has some new firmware available for this that I don't have. I haven't gone and updated my CF card in a little bit. Pick 220, I guess. I don't know what you want to do. Let's just save our character, saving configuration. Okay, I hit Control-Delete, and it's still playing the notes. Well, CMS can sound good sometimes. I think it has 22 channels of square wave audio, and it is stereo, which is the OPL2 on the original Sound Blaster is not. So you get stereo sound, but it didn't sound a bit harsh. I'm not 100% convinced the CMS sound out of the PicoGus, or at least with the firmware I'm using, is totally authentic. It sounds a little harsher than I remember. My 5170 has a real Sound Blaster 1.5 in there with the CMS chips installed, like the PAL and the 2 Philips sound chips or whatever it is. It sounds pretty good, and some games really use it to good advantage. It's a real kind of more 8-bit sound than the FM stuff is. It's less smooth because it is square waves. Anyway, what I really wanted to see is if this 286 board is working after the, you know, quote unquote not repair. And yeah, it works great. So there we have it. I think this is a pretty decent little motherboard. The fact that 0 weight states makes it cool. It's small, late model, and flexible with the RAM. Of course, we have these stupid SIPs, which we've talked about before. I don't like them, but we could swap the sockets out, or I could make more SIPs by taking normal 30-pin SIMs and just soldering some pins onto it. And then I'd be able to upgrade this to 4 megabytes if I so desired. But I kind of like that it's flexible, and hopefully this cleanup work that I've done here should keep this thing working for the, well, I don't know, indefinite future. I'm pretty confident that I've cleaned up enough of the corrosion off this board that there shouldn't be any more problems with it getting worse. It's still possible because obviously I didn't go underneath all the chips, but I'm pretty confident and I'm happy with the way this looks. I even like that copper look to the exposed traces, even though there's nail polish on there now. And yeah, you got to see me do this mod with the battery and get tripped up by the Schottky diode and all that kind of stuff. But I think the little mod that I've done here is perfect. And I'll obviously be storing this without the battery installed, mainly because, you know, these CR2032s aren't free, and there's no reason to leave it in here. This is going to be put back in an anti-static bag, and it'll be one of my spare motherboards. So that's it for this video. Hope you liked it. Sorry it was a bit all over the place, but it's kind of how it goes for the second channel. As I mentioned at the beginning, by the way, I was planning to do a repair of this, and it didn't need it in the end. Just needed this sort of cleanup work, which is what I did here. So if you liked this video, thumbs up. If you didn't, you know what to do. Thanks to my supporters. Names going up beside the screen. And, you know, all the usual YouTube junk, and I guess that's going to be that. So stay healthy, stay safe. I'll see you next time. Bye.